Greetings of the day to all of you. Today we are going to discuss how to calculate RMS Stator Flux Ripple. So I will write here RMS Stator Flux Ripple. We'll see how we can make calculations and calculate the stator flux ripple. Right. Let us revisit or what we have discussed in last class. In our last class, we discussed how to draw the stator flux ripple, waveform, and how this stator flux ripple varies in different time intervals. For example, if I draw a space vector diagram, this is my alpha axis, this is beta axis, right? So this is my active vector 1, which is applied across the load for time interval t1. Before that, we apply null vector, and this is null vector 0, which is applied for time tz by 2. Active vector 1 is applied for time interval t1, and then this is active vector 2, which is applied for time interval t2. Okay, so the sequence is 0, 1, 2, and then we have another null vector 7, which is also applied for time interval tz by 2. So the sequence is like this: 0, 1, 2, 7, and then 7, 2, 1, 0. That's the sequence. The reference vector will be somewhere here. For example, the reference vector may be here. This may be the reference vector vref. I will write here vref. Fine. Now when reference vector vref is applied, so this is our q-axis. So let me extend it a bit, and our d-axis is at 90 degrees to q-axis. So this is d-axis, but I can show this d-axis somewhere here. So this is our d-axis, and this is the origin. Now we already know that when null vector 0 is applied across the load, the desired voltage vector across the load is vref, the applied voltage vector is 0. So therefore there is an error voltage vector Vr. So therefore I will write here the null vector 0 with switching sequence minus 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 is applied. So error vector is error voltage vector is the applied vector minus reference vector. I mean, it is applied vector is 0, its length is 0, so it is minus vref. Okay, so it is minus vref. This is the error voltage vector. Now when we resolve this error voltage vector into d component and q component, right? So its d component will be, or its q component of this error vector will be, okay? So the q component is, see, it is what is actually applied. What is actually applied is null vector whose length is 0. So it is 0 minus what is the desired reference vector along q-axis. You can see along q-axis vref itself is applied. So it is 0 minus vref, it is equal to minus vref. So this is the q component of this error voltage vector. And what about its d component, vd tilde? D component will be along this axis. Okay, along this axis, what we apply? We apply 0 vector 0 or null vector 0. So it is 0 minus what is the component of this desired voltage vector along d axis. Since these two axes, v reference is along q axis and this is d axis, they are 90 degrees with respect to each other. So it is 0. So it is 0 minus 0 means 0 itself. So therefore, when null vector 0 is applied, okay, then the q vector, q axis component of error voltage vector is minus vref, and d axis component of error voltage vector is 0. Fine, we already know this. This is just the recap of what we have done in the last class. Let us see what happens when active vector 1 is applied. So active vector 1 with switching sequence plus minus minus. When this active vector 1 is applied, so this is our desired vector and this is the applied vector. So therefore this will be error voltage vector VR, V error. Now this error voltage vector V error will be applied voltage vector, which is V1 or VDC minus reference voltage vector Vref. Let me now resolve it into D and Q components. Okay, so the error voltage vector along Q axis VQ tilde is equal to, along Q axis what are we applying? We are applying active vector 1. Active vector 1 is along alpha axis and its component along Q axis is, its length is VDC and active vector 2's length is also VDC. So VDC is applied, active vector 1 with magnitude VDC is applied along alpha axis and its component along Q axis is VDC cos theta s, because this angle is theta s. So it is VDC cos theta s minus the desired vector along Q axis. What is desired vector along Q axis? That's Vref. So this is the Q component of, error voltage vector along Q axis. What about error voltage vector component along D axis? Vd star. Along D axis, what is the applied voltage vector? Applied voltage vector is 1, which is VDC, and its component along D axis is VDC sine theta s. So it is VDC sine theta s minus the desired voltage vector. Desired voltage vector is along Q axis. Its component along D axis is 0 because these two axes are 90 degrees apart. So it is minus 0. So that means Vd tilde is equal to VDC sine theta s. So just remember it. So shall I write it here? I should write it. So VQ is equal to VDC cos theta s minus Vref, and Vd tilde is equal to VDC sine theta s. This is when active vector 1 is applied. Okay. Now let us see what happens when active vector 2 is applied. Now we are applying active vector 2 across the load. Active vector 2, which has a switching sequence of plus plus minus, when this is applied. Okay. When active vector 2 is applied, this is our active vector 2. So this is the applied vector and this is the desired vector. So therefore error is this. This is the error vector VR. So what is this error voltage vector VR? It is what is actually applied. What we actually apply is active vector 2, whose length is VDC, minus what is the reference vector? Reference vector is Vref. So it is VDC minus Vref. Okay. Now let us resolve it into Q and D components. So along Q axis, it will have a component VQ tilde equal to. Now active voltage vector along Q axis, active voltage vector has a length of VDC and its component along Q axis, this is Q axis, will be VDC cos of 60 degrees minus theta s. It is because of the fact that this total angle is 60 degrees. This is theta s. So this angle will be 60 degrees minus theta s. So therefore it is VDC cos theta s minus, so this is the component of active vector along Q axis, VDC cos 60 degrees minus theta s minus reference vector Vref. Fine. And what about component of error voltage vector along D axis? So along D axis, so this is our D axis if you take it, if you extend it in the other direction. Active vector 2 is applied. Okay, its component along D axis will be VDC sine of 60 degrees minus theta s. Okay, in fact it will be minus VDC because this is plus D axis and this is minus D axis. So it is minus VDC sine of 60 degrees minus theta s minus what is the component of this reference vector along D axis. Since this angle is 90 degrees, so it is minus 0. So therefore this is the D axis component of error voltage vector when active vector 2 is applied. I will write it here. So the Q component of error voltage vector when active vector 2 is applied, it is equal to VDC cos of 60 degrees minus theta s minus Vref, and d-axis component of error voltage vector when active vector 2 is applied is minus VDC sine of 60 degrees minus theta s. That's it. This is when active vector 2 is applied. Right. So this is just a revision of what we have done in last class. So therefore, when null vector is applied, we know at that time the component of error voltage vector along q-axis is minus Vref, and it has no component along d-axis. When active vector 1 is applied, the error voltage vector along q-axis is VDC cos theta s minus Vref, and the error voltage vector along d-axis is VDC sine theta s. Similarly, when active vector 2 is applied, the q-axis component of error voltage vector is VDC cos of 60 minus theta s degrees minus Vref, and d-axis component of error voltage vector is minus VDC sine of 60 minus theta s degrees. Fine. Now with this knowledge, let us now, once we know the components of these error voltage vectors, d components, q components, later on we'll be using them in certain equations for calculating RMS stator flux ripple. But before that, I have already told you when these error voltage vectors, so this is error voltage vector when null vector is applied. This is the error voltage vector when active vector 1 is applied, and this is the error voltage vector when active vector 2 is applied. When I integrate these error voltage vectors, so I get stator flux ripple vector. And this stator flux ripple vector is when null vector 0 is applied. So when null vector 0 is applied, it grows in this direction. Okay, so it grows in this direction, and at the end of 0.5 tz, that is tz by 2, then we apply active vector 1. So when active vector 1 is applied, you can see active vector 1 is in this direction. So when I integrate this, this error voltage vector is in this direction when active vector 1 is applied. When I integrate this error voltage vector, I get a line parallel to this like this. Okay. So this is when active vector 1 is applied. And this active vector 1 is applied for a time interval of t1. So total time interval is 0.5 tz plus t1. After that, we apply active vector 2. When active vector 2 is applied, this is the error voltage vector. And when I integrate this error voltage vector, I get a flux ripple, stator flux ripple vector, which grows in this direction, in a direction which is parallel to this. So it is like this. So this is when active vector 2 is applied. And active vector 2 is applied for a time interval t2. So total time is 0.5 tz plus t1 plus t2. And then we apply null vector 7. And when null vector 7 is applied, we go back to this, move back to origin. So therefore our stator flux ripple vector is psi tilde. So when null vector is applied, it moves along this line. When active vector 1 is applied, it moves along this line. When active vector 2 is applied, it moves along this line. And when null vector 7 is applied, again it moves along this. And this is what happens in one subcycle. So it starts from here, moves like this, goes back to the origin. Fine. So this much of knowledge we already have. We have done it already in the last class. And this is just a repetition of what we have already learned in last class. Now, our aim is to find the stator flux ripple vector. We have a stator flux ripple. We will resolve it into D component and Q component, and we will find the D component stator flux ripple and Q component stator flux ripple. Okay, and that will give us an idea about a ripple in the current when a particular PWM technique is applied. Fine. So I will reproduce this diagram here. So this is our D axis and this is our Q axis. So it is 0 vector, vector 1, vector 2 and vector 7. Okay, so we already know it. This is the D axis. So this is my error voltage stator flux error vector, which moves like this. Now if I resolve it into Q components and D components and draw those Q and D components as a function of time, it will be something like this. This is time axis. Let me first of all draw psi d tilde. That is the component of this stator flux ripple vector. This is the stator flux ripple vector which moves along this triangle. Its component along d axis is psi d tilde. Okay. Now it is very interesting to see that when null vector 0 is applied. This is the this is our stator flux ripple vector. It moves along this, and it has no component along d axis. Since we are trying to now draw the d axis component of the stator flux ripple vector, so when null vector is applied, our stator flux ripple vector moves in this direction along q minus q, and it has no component along d axis, so therefore it has no component along d axis. Okay, this is for time interval t naught equal to 0.5 tz, and then we apply active vector 1. When you can very clearly see when active vector 1 is applied. Now stator flux ripple vector, it was maximum negative here, so it becomes less negative now, and here it becomes 0, and then it grows in the positive direction. So I mean along d-axis, if you find it is d-axis component, so along d-axis it increases like this. It starts from 0 and then it increases along d-axis like this. So therefore it will grow, or it will rise like this. So this is when active vector 1 is applied. Here active vector null vector 0 is applied, and during this interval active vector 1 is applied. Fine. And what is this time interval? This time interval is t1 for active vector, for which active vector 1 is applied. Then we apply active vector 2. You can very clearly see when active vector 2 is applied, its d-axis component, you can see it decreases and then it becomes 0 like this. So therefore it comes down, it becomes 0 here. This is there for time interval t2, the active vector 2. And then we again apply null vector 7. So our stator flux ripple vector moves along this axis, along q axis like this, and it has 0 component along d axis. So this is when active vector 7 is applied for again time interval t7 equal to 0.5 tz. So it is again 0. So it is 0 for 0.5 tz, it is 0 again for 0.5 tz when null vectors 0 and 7 are applied. When active vector 1 is applied, it moves like this. When active vector 2 is applied, it moves like this. Okay. Now we know that when active vector 1 is applied, so let's have a look at these equations. When active vector 1 is applied, the d component of this error voltage vector is VDC sine theta s. Okay. And if I multiply this VDC sine theta s by time interval t1, that will give me length of this d component stator flux. It will give me the height or length of this line. So let me call that height as d. So therefore I can write d is equal to VDC sine theta s into t1. I repeat, when active vector 1 is applied, okay, we have an error voltage vector, and the error voltage vector is like this, and its d component grows like this. When null vector was applied, error voltage vector was 0. D axis component of error voltage vector was 0. When active vector 1 is applied, d axis component of error voltage vector is like this. And what is the height, or what is the length of this line? We already know, we have just few moments back found that when active vector 1 is applied, the d-axis component of ripple voltage vector, the d-axis component of error voltage vector is VDC sine theta s. So this is VDC sine theta s, and this vector is there for time interval t1. So if I multiply it by t1, VDC sine theta s multiplied by t1, that will give me d. Okay. So keep it preserved for the time being because I require it later on. Fine. So this is about psi d tilde. What about psi q tilde? That is the q-axis component of stator flux ripple vector. Let us draw that q-axis component. This is again time axis. Now you can very clearly see when null vector is applied and then active vector 1 is applied, then active vector 2 is applied, then again null vector is applied. Now when null vector 0 is applied for time interval 0.5 tz, you can see my stator flux ripple vector moves in this direction. This is my positive q-axis, it moves in the negative direction along q-axis. So therefore it grows like this up to this point, right? After that we apply active vector 1, and active vector 1 is applied. See, when at the end of 0.5 tz time interval, my this vector is maximum negative. Stator flux ripple vector is maximum negative, and when null vector 1 is active vector 1 is applied, it becomes less and less negative, and then it becomes 0, and then it becomes positive. So therefore it first becomes less negative, then it becomes 0, and then it becomes positive. So this is when null vector 0 is applied, this is when active vector 1 is applied. This is the q-axis component of stator flux ripple vector. Fine. After that we apply active vector 2. Now we can very clearly see when active vector 2 is applied, it is something like this. The q-axis component of this stator flux ripple vector is more or less constant. It grows very slowly, it's almost constant. This is when active vector 2 is applied. Okay. After that we apply active vector 7 again. When active vector 7 is applied, my stator flux ripple vector moves in this direction and it goes back to origin, it goes back to 0. That means it goes down and becomes 0 again when null vector 7 is applied. So this is the q-axis component of stator flux ripple vector when different states, switching states are applied. This is when null vector is applied, this is when active vector 1 is applied, active vector 2 is applied, and null vector 7 is applied. This is the q-axis component of stator flux ripple vector. Fine. Now I am interested in finding the length of this line, similarly the length of this line, and all other lines, because later on I will be using these lengths of the lines for calculating the stator d-axis and q-axis stator flux ripple vector. Now from this diagram you can see when null vector 0 and null vector 7 is applied. Now this null vector 0 is applied for a time interval t0, and null vector 7 is applied for a time interval t7. And what is t0? t0 is tz by 2, and t7 is also tz by 2. So therefore this is t0, this is t7, so this is tz by 2 plus tz by 2. So total time interval is tz by 2 plus tz by 2 is tz. Fine. So let us define some quantities. Let us define, first quantity is qz. Qz will be the component of error voltage vector which is there when these two null vectors are applied. When null vector 0 is applied and then null vector 7 is applied. For that I will move to these equations. Okay. You can see when null vector 0 is applied. For example, when 0 is applied, just few moments back we have seen that it's the D component of error voltage vector is 0 and Q component of error voltage vector is minus V ref. So that means when null vector 0 is applied, or similarly when null vector 7 is applied, it has no D component but it's a Q component which is equal to minus V ref. So therefore QZ will be equal to minus V ref into, for how much time these two null vectors are there? They are for a time interval Tz. So this is minus V ref into Tz. So this is called QZ, it's volt second. Okay, and this volt second, this is the voltage, error voltage vector which is applied when these two null vectors are applied. This is the total error voltage vector, and this error voltage vector is there for Tz by 2 plus Tz by 2, that is Tz time interval. And this minus V ref into Tz, incidentally it gives the length of this line, height of this line or length of this line, and it is, I will write here, it is 0.5 QZ. Because what is my total time interval? Total time interval is Tz. When null vector 0 is applied, what is time interval? It is Tz by 2. So therefore this will be minus V ref into Tz by 2, that is 0.5 QZ. Okay. So therefore, when null vector 0 is applied, the length of this line is 0.5 qz. Fine. After that, we will define q1. q1 means when active vector 1 is applied. You can very clearly see when active vector 1 is applied. This active vector 1 is applied for a time interval t1. And you can see from these equations, when active vector 1 is applied, what is the q component, q axis component of voltage vector, error voltage vector? When active vector 1 is applied, what is the q axis component of error voltage vector? Error voltage vector q axis component I have already written here. It is VDC cos theta s minus Vref. So I will write here VDC cos theta s minus Vref, and it is there applied for a time interval t1 because active vector 1 is applied for time interval t1. So therefore, the length of this line will be given by q1, and total from here to here is 0.5 qz plus q1, right? So that means if this is 0.5 qz, this will be 0.5 qz plus q1, where q1 is this. Okay. After that, active vector 2 is applied. When active vector 2 is applied, the volt second is given by. Now this active vector 2 is applied for time interval t2. Now what is the q axis component of error voltage vector when active vector 2 is applied? Go back to this equation. When active vector 2 is applied, the q axis component of error voltage vector is VDC cos of 60 minus theta s degrees minus Vref. So it is VDC cos of 60 minus theta s degrees minus Vref, and this error voltage vector is there for time interval t2. Okay, so that is q2. So therefore this will be here 0.5 qz plus q1 plus q2. So here it is 0.5 qz, 0.5 qz plus q1, and this will be then 0.5 qz plus q1 plus q2, where q2 is this. And then null vector 0 is again applied. We reach here, and here it will be 0.5 qz plus q1 plus q2 plus 0.5 qz again. That's it. So therefore we have been able to write the lengths of these lines, the magnitudes of these linear lines in terms of equations, in terms of q axis components of voltage vectors. Okay, so with this knowledge, we are now ready to determine the stator d axis and q axis stator flux ripple vectors. It's now easy to find d axis and q axis stator flux ripple vectors. RMS value. Now before we do that, how do we find RMS value? First of all, RMS value means root of mean square. First of all, what you will do, these linear lines you will square. For example, I have a linear line here, 0 to d. If I square it, it gives me a parabola like this, d square. Similarly, this linear line, when I square it, it gives me another parabola like this. Then what I will do, I will find area under this parabola, because root mean square means root of mean, square root of mean square. Once you have squared these lines and you have got parabola, then you have to find mean of those square. And how do you find mean of square? By finding area under this parabola. This is the square, d square. So this is my parabola, and area under this parabola is mean of square. Similarly, on this side, this is another parabola, and when I find area under this parabola, that gives me mean of square. Okay, so that can be very easily found. I told you in the last lecture also, if you find the area of this rectangle, and if you find area of this rectangle, if you find area of these two rectangles or area of this total rectangle, divide that by 3, that will give you total area under these two parabolas. So that will give you mean of square. That is for psi d tilde. What about psi q tilde? Psi q tilde, in psi q tilde, first of all, you will have this line. This is piecewise linear, curve. First of all, you have this line. Find square of this. When you find square of this line, you get parabola like this. You get a parabola, something like this. Parabola. Okay. Then you square this line. When you square this line, you find another parabola, something like this. Then you square this line. When you square this line, there is another parabola like this. And finally, you square this line. When you square this line, you finally get this parabola. So find area under this parabola, find area under this parabola, area under this parabola, and area under this parabola. When you find area under these all parabolas, you will be find mean square of psi q tilde. And then you can take square root of whole quantity, that will give you RMS value of psi q tilde. Similarly, you will find RMS value of psi d tilde. So how to do that? Let us see. Let us see how to do that. First of all, I will write here RMS d-axis stator flux ripple. Now I have a stator flux ripple. I have found its d-axis component and q-axis component. So how to find RMS value of d-axis stator flux ripple? This is my d-axis stator flux ripple. I have to find its RMS value. Similarly, I have to find RMS value of q-axis stator flux ripple. Stator flux ripple. I have to find RMS value of q-axis stator flux ripple. Where is q-axis stator flux ripple? This is the q-axis stator flux ripple. I have to find its RMS value. Okay. How do you find RMS value? For example, how do you find RMS value of d-axis stator flux ripple? You first find square of these lines. So square of this line and square of this line gives two parabolas. Then you find area under these parabolas. That will give you mean of square. And then when you take square root of that, that will give you RMS value of d-axis stator flux ripple. Similarly, if you want to find RMS value of q-axis stator flux ripple, you square of all these lines. This is subinterval 1, subinterval 2. You divide it into 4 subintervals, 1, 2, 3, and 4. So for subinterval 1, you square this line, you get a parabola. For subinterval 2, you square this line, you get another parabola. For subinterval 3, you square this line, you get another parabola. And for subinterval 4, you square this line, you get parabola. Find area under all these parabolas. That will give you mean of square, and then take square root of whole of thing. That will give you RMS value of q-axis stator flux ripple. Now the question is how to find area under these parabolas. In order to understand or in order to develop a generalized equation for finding areas under these parabolas, let us take a simple mathematical equation of a straight line. This is my straight line. For example, the straight line is given by equation y equal to mx plus c. Fine. This is a very well-known equation of a straight line mx plus c, which is given here. I will take two time intervals. I will take x1 value, and at x1 instant, the value of the magnitude of this line or the value of this line is y1, and at time interval or at instant x2, the value is y2. So at x1, the line has a value of y1, and at x2, the line has a value of y2. So therefore, when I square this line, so what are we doing actually here? We have straight lines like this, which are given by y equal to mx plus c equation. But in order to find RMS value, you have to first square these lines. So let us square this line also. So when I square this line, that will give me parabola. So therefore, I will write here parabola becomes, when I square these lines, so that is equal to y square, that is equal to mx plus c whole square. Okay, so when you find the parabola, when you square this line, you get equation of parabola y square equal to mx plus c whole square. After that, you have to find area under the parabola. For example, you have to find area under all these parabola. Let us try to develop an equation for finding area under parabola. So I will write here area will be equal to, how do you find area? You just integrate this parabola. So what I will do, I will integrate this parabola. Equation of parabola is mx plus c whole square. I will integrate it from between the limits x1 and x2. So I want to find area within this time interval x1 to x2. So my limits of integration are x1, x equal to x1, or let me write here x1 and x2. So what does integration give? What is the integration of mx plus c whole square? The integration of mx plus c whole square is mx plus c whole cube by 3m. And the limits of integration are x equal to x1 and x equal to x2. Fine. Let us further simplify it. Now it is mx plus c whole cube. What is mx plus c, by the way? Mx plus c is, it is y, because just few moments back we have written y equal to mx plus c. And if I add x equal to x1, at x equal to x2, it is mx2 plus c whole square. So it will be y2 equal to mx2 plus c. And when I put x equal to x1, I get mx1 plus c, that will be equal to y1. So therefore this will be equal to, this will be y2 cube, okay, this will be y2 cube 1 by 3m y2 cube minus y1 cube. First I am putting x equal to x2, that gives me y2, so it is y2 cube, minus then x equal to x1, that gives me y1 minus y1 cube. Fine. Okay, so then that comes out to be, if I further solve it, simplify it, this is y2 cube minus y1 cube. I can write it like this, y2 minus y1 by 3m, and inside I will have y2 square plus y2 y1 plus y1 square. I am expanding. I have y2 cube minus y1 cube. I can write y2 cube minus y1 cube like this, y2 minus y1 into y2 square plus y2 y1 plus y1 square. I am expanding it. So I can write it like this also. Product of y2 minus y1 and y2 square plus y2 y1 plus y1 square. Right. So what is this y2 minus y1? y2 is the value at x2. So therefore I can write area equal to, instead of writing y2, I can write x2 minus x1 by 3 into y2 square plus y2 y1 plus y1 square. Why I have written x2 minus x1? Because y2 is the value at x equal to x2 and y1 is the value at x equal to x1. So I can write x2 minus x1 divided by 3 into y2 square plus y2 y1 plus y1 square. Just remember this formula. I can write this area formula here. Area is equal to x2 minus x1 by 3 into y2 square plus y2 y1 plus y1 square. I will be using this formula in computing the RMS value of stator flux ripples. Now with this background, we are now ready to find RMS value of stator flux ripple. Let us try to find RMS d-axis stator flux ripple. My d-axis stator flux ripple is given by this. If you have to find its RMS value, how can we find? We can find, first of all, you have to square this line. RMS means root means square. So square, first step is square. When I square this, I get parabola. When I square this line, I get another parabola. Okay, so after squaring, I have to find area under the parabola. Okay, the area under parabola is given by generalized formula x2 minus x1 by 3 into y1 square plus y1 y2 plus y2 square, like this. So therefore area will be, it is x2 minus x1 by 3. x2 minus x1 means, total time. See, what is your total time? This active vector 1 is applied there for time interval t1. Active vector 2 is applied for time interval t2. So x2 minus x1 is basically this total time interval. So this is t1 plus t2 by ts. So this has to be divided by ts because total this total time period is Ts. This is sub-cycle interval. So therefore, out of this sub-cycle Ts, what is the time for which active vector 1 and active vector 2 is applied? It's T1 plus T2. So the total time for out of the sub-cycle time Ts, the time for which T1 and T2 is applied is T1 plus T2 by Ts. And then this is divided by 3. So I will write 1 by 3. Okay. Into, it is y1 square plus y2 square plus y2 y1. I have only one here. I have only one length here. Length of this line or length of this line is d. So it is simply d square, nothing else. Okay. So therefore, this is equal to, so therefore I can write area is equal to, so I can write 1 by 3, then d square into T1 plus T2 by Ts. I can write it like this also. So this gives me RMS d-axis stator flux ripple. Okay. Once you know area, then you have to take square root of this. Okay. Let me call this psi d tilde. Okay. Iska area. Then how do you find its RMS value? So RMS value will be, let's call this psi d. That is under root of psi d tilde. Okay, that's under root of all this. That is equal to square root of 1 by 3 into d square T1 plus T2 by Ts. What is this 1 by 3 d square into T1 plus T2 by Ts? It is the area under this parabola. It is the mean square. Okay. And now you have to find RMS. Root means square of square root of mean square. Mean square is this, and take square root of this. That will give you RMS value of this. Okay. So what is this d? D, I have already told you, d is VDC, where these quantities, where d is equal to VDC sine theta s minus T1. We already know. What is time interval T1? If you remember, time interval T1 is Vref. I should write it somewhere here. Let me write equation for time interval T1. It is Vref sine of 60 degrees minus theta s by VDC sine 60 degrees into Ts. This is the equation for dual time T1, which we have determined in one of the earlier classes. We already know. What is dual time T2? T2 is equal to Vref sine theta s by VDC sine 60 degrees into Ts. Okay. So d is given by VDC sine theta s minus T1, and T1 is given by this equation, and T2 is given by this equation. We know all these equations. Substitute here. Take square root of this. That will give you RMS value of d component stator flux ripple. Stator flux ripple d component RMS value will be given by this. Fine. So once you have found RMS value of stator flux ripple, d axis component of stator flux ripple, it's now time to find RMS value of stator q axis component of stator flux ripple. So I will write now RMS q axis stator flux ripple. Okay. For that purpose, what I will do, I will divide this. This is my q-axis stator flux ripple total. So I have to find RMS value of q-axis stator flux ripple. So I have so many parabolas. I have this parabola. This is square of this. I have already squared it. I have this parabola, which is square of this line. I have this parabola, which is square of this line. And finally, I have this parabola, which is square of this line. Okay. So first of all, I will take this parabola. Okay. And I will find area under this parabola. That will give me mean square. Let us call that subinterval 1. Then I will take subinterval 2. In subinterval 2, I will take active vector 1. और इसका parabola ये है, इसका area under this parabola I will find. Similarly, in subinterval 3 I will find area under this parabola, and in subinterval 4 I will find area under this parabola. So I will do it subinterval type wise. So I will take first subinterval. In first subinterval, situation is like this. This is time axis and this is psi q tilde. Okay, so null vector 0 is applied. So this is null vector 0. Okay, and this is there. The height of this line is 0.5 qz. We already know. Okay, and when I square this line, I get a parabola like this, and I get a parabola like this, and I have to find area under this parabola. So let me call that area under this parabola as Q1. Now Q1 is given by, I'm sorry, I should not have erased that formula. What is the formula for finding the area? I will write that formula again. Area is given by x2 minus x1 by 3 times y1 square plus y1 by 2 plus y2 square. Okay, use this formula here. So area under this parabola is given by this formula. What is this x2 minus x1? x2 minus x1 is the total time interval. And what is the total time interval? Total time interval is 0.5 tz. क्योंकि आप देख सकते हैं यहाँ से यहाँ तक null vector, we are applying null vector, and this time interval is 0.5 tz. ये time intervals, this whole time interval is 0.5 tz. So therefore x2 minus x1 is nothing but it is 0.5 tz divided by ts. It is what is total time interval? Total time interval is ts, out of which null vector is applied for time interval 0.5 tz. So the time interval x2 minus x1 is 0.5 tz by ts. Then it is divided by 3 also. So I will write this 3 also. Multiplied by what is inside. If you have two quantities, y1 square, y1 and y2, but we have only one quantity, that is 0.5 qz. So I will write here 0.5 qz. It is y1 square only, so it is 0.5 qz whole square, right? So therefore, I will write here, therefore q1 is equal to, 1 by 3, I can write it like this, 1 by 3 into 0.5 qz whole square into 0.5 tz by ts. This is the same equation. I am writing it like this. So this is my Q1. This is the area under first parabola, this parabola. Fine. This is in first subinterval. Let me take second subinterval. Second subinterval. In second subinterval, it's like this, time axis, and this is psi q tilde. In first subinterval, it was 0.5 qz. In second subinterval, I mean null vector 0 was applied, and then null vector 1 is now applied. And what is this length of this vector? It is 0.5 qz plus q1, and q1 equation we have already noted down just few moments back. And this time interval is 0.5 tz, and this time interval is time interval t1. So this active vector 1 is now applied. It's applied for time interval t1. Or when I square this, I get parabola like this, something like this. I get something like this. Now I have to find area under this parabola. So let me call that area as Q2. Q2 is equal to x2 minus x1 by 3. That is given by x2 minus x1 by 3. x2 minus x1 means this total time interval for which this active vector 1 is applied. Now you can very clearly see active vector 1 is applied for time interval t1 by ts. So it is t1 by ts. And since it is divided by 3, so it is t1 by 3 ts into y1 square. Now it has two parameters. It has its minimum value is 0.5 qz and its maximum value is 0.5 qz plus q1. So this is, you can say, y1 and this is y2. So it is y1 square. Y1 square is 0.5 qz whole square plus y1 into y2. y1 is 0.5 qz into y2. y2 is this maximum value, 0.5 qz plus q1 plus y2 square. y2 is again this value, 0.5 qz plus q1 whole square. That's it. This is my q2. This is what I get in second subinterval. Let us quickly go to third subinterval. Third subinterval. In third subinterval, active vector 3 is applied. I can show that here. First, null vector 0 was applied. Okay. Then active vector 1 was applied. And then active vector 2 is applied. When active vector 2 is applied, something like this. Sorry, something like this. Now, what is this? This is 0.5 qz plus q1. And what is this? This is 0.5 qz plus q1 plus q2. We already know, we have just a few moments back drawn it. And this is the time interval t2 for which active vector 2 is applied. For this time interval, active vector 2 is applied. Now, as far as, so this is your, so you can call this y1 and this is your, this is your, okay, anyway, this is your, this is your y1 equal to 0.5 qz plus q1 and this is y2 equal to 0.5 qz plus q1 plus q2. So, y2 is equal to 0.5 qz plus q1 plus q2. Now, we know that q1 plus q2 plus qz is equal to 0. So, that means q1 plus q2 is equal to minus qz. Substitute here. So, therefore, y2 will be equal to 0.5 qz plus q1 plus q2. q1 plus q2 is minus qz. So, minus qz. So, what is 0.5 qz minus qz? That is equal to minus 0.5 qz. So, therefore, this y2, which I have written as 0.5 qz plus q1 plus q2, it is basically, it comes out to be minus 0.5 qz. So, I can write here y2 equal to minus 0.5 qz after, simplification. So, apply the formula and find area under this. This is the parabola. You have to find area under this parabola. Let me call that area as q3. q3 is equal to, x2 minus x1 by 3. x2 minus x1 is time interval. Time interval for which active vector 2 is applied is t2 by ts. So, it is t2 by 3 ts because it is divided by 3 also. Then y1 square. What is your y1? y1 is 0.5 qz plus q1. 0.5 qz plus q1 whole square plus y1 y2. y1 is this and y2 is this. That is 0.5 qz plus q1 into y2. y2 is minus 0.5 qz. This is minus 0.5 qz. Okay. Plus y2 square. y2 is again minus 0.5 qz whole square. That's it. This is the area under this parabola in subinterval 3. Then we have last subinterval. Fourth subinterval. Fourth subinterval. I will again draw this psi q tilde. It's like this, null vector, active vector 1, active vector 2, and then null vector 7 is applied. And we know that this null vector 7 is applied for time interval 0.5 tz. What was this value? This was just few moments back. We found that this value was minus 0.5 qz. Okay, this was minus 0.5 qz. Right. Then value here is 0. So therefore, area, so when you find square of this, you'll find this, it will give you a parabola. And what is area under this parabola? Let's call that area as Q4. That is equal to x2 minus x1 by 3. x2 minus x1 is basically time interval for which this null vector is applied. And you can very clearly see this null vector is applied for a time interval 0.5 tz, which is also tz by 2. Okay, so it is tz by 2 into 1 by 3. In fact, it is tz by 2 ts. Okay, it is tz by 2 into ts. Okay, into 1 by 3. And then what is, this is y1, this is y2. y2 is 0. y1 is 0.5 minus 0.5 qz whole square. So I can write Q4 equal to tz by 2 into 1 by 3 ts like this into 0.5 qz whole square. That's it. This is area under this parabola. Now once you know area under all parabolas, okay, so therefore RMS Q-axis stator flux ripple is, it is given by, let's call this psi q, and write RMS, psi q RMS is equal to, so RMS value of Q-axis stator flux ripple is equal to stator flux mean square, that is the area under first parabola Q1 in first subinterval, plus in second subinterval the area under parabola is Q2, plus in third subinterval the area under parabola is Q3, plus in fourth subinterval, for example here, this is the area under parabola, area under this parabola Q4. So these are all mean squares, and then you take square root of all this, so that will give you RMS value of Q-axis flux ripple. Fine. Now you know D-axis flux ripple, stator flux ripple, you know Q-axis stator flux ripple. So therefore psi RMS, I mean total stator flux ripple square is equal to psi D RMS square plus psi Q RMS square. Okay, so that will give you total stator flux ripple, which is given by this. So this will give you total stator flux ripple psi RMS equal to, that will be under root of psi D square RMS plus psi Q square RMS. That's it. Now you have already developed equations. You have equation for psi D RMS. And what was that equation for psi D RMS? We found it earlier, just 2 moments back. It is 1 by 3 d square t1 plus t2 by ts whole square and square root of that. And psi Q RMS, just few moments back we have found. Take square of that, take square root of all of this, square root of psi D square RMS plus psi Q square RMS, that will give you total stator flux ripple. So this gives stator flux ripple. And interestingly, the stator flux ripple is a measure of current ripple, the ripple in the current flowing in the windings of an induction motor, because the flux is directly proportional to current, and if you are able to find stator flux ripple, this stator flux ripple is a measure of stator current or load current ripple. This is of course in dq axis. What you have to do, you have to go back from dq to alpha beta transformation, and then from alpha beta to ABC transformation, and then you will have psi A RMS, phase A RMS, psi B RMS, and psi C RMS, and for phase A, phase B, phase C. And this will directly give you IA RMS, phase current A RMS, I mean a ripple. You have to write ripple, you have to put tilde, IA RMS tilde, IB RMS tilde, and IC RMS tilde. So once you know phase A, phase B, phase C, stator flux ripples, and that will directly give you measure of line current A, line current B, and line current C ripples. This is line current A ripple, line current B ripple, line current C ripple, and this is the method of calculating that. Okay. And now my final remarks of today's lecture is that just few moments back we found psi d RMS. Okay, the RMS value of d-axis stator flux ripple, and we have found that it is a function of three things. It's a function of reference vector Vref, it's a function of angle of reference vector spatial angle theta s, and it is also a function of ts, the sub-interval time period. Go back to that equation, and shall I write that equation again for your reference? Let me write that equation. We had found this psi d RMS. We had found equal to under root of 1 by 3 d square t1 plus t2 by ts, where t1 I already told you it is Vref sine of 60 degrees minus theta s by VDC sine 60 degrees into ts, and dwell time t2 is Vref sine theta s by VDC sine 60 degrees into ts. Now t1 is a function of Vref and ts, t2 is also a function of Vref and ts. So, and now therefore psi d RMS is a function of, you can see it's a function of Vref, because Vref is there in these equations. It's also a function of theta s, because theta s is also there. It's also a function of ts. It's a function of three parameters: reference vector, rotating reference vector Vref, spatial angle theta s, and subinterval time ts. Psi q ripple is also a function of psi q RMS, that's RMS value of q axis stator flux ripple, is also a function of these parameters Vref, theta s. Go through the equations, and from those equations we will find it. And finally, the total RMS, the total flux ripple, I mean stator flux ripple, which is under root of psi d square RMS plus psi q square RMS. When these psi d RMS and psi q RMS are a function of these three parameters, the total stator flux ripple will also be a function of Vref, theta s, and ts. And finally, I will write this psi RMS like this. This RMS stator flux ripple can also be written in the form of this equation: C naught Vref square plus C1 Vref cube plus C2 Vref raised power 4 into ts. Okay, we'll discuss about this equation in next lecture. So I will end my today's lecture. So in today's lecture we have seen how we can find stator flux ripple in a plane, dq plane, and how can we then find the d-axis component of stator flux ripple and q-axis component of stator flux ripple. Having done that, we have seen how we find the d-axis stator flux ripple RMS value and q-axis stator flux ripple RMS value using those equations. Okay, and finally how to find the total stator flux ripple. And then we have also seen that the stator flux ripple is a function of three parameters: rotating reference vector Vref, spatial angle theta s, and subinterval time ts. And finally, this psi RMS can also be written in the form of this equation. We'll discuss more on it in next lecture, and slowly we are building the basic concept. We have seen at the end of today's lecture, we are now able to find the stator flux ripple RMS value of total stator flux ripple. Okay, now we are in a position to find the RMS value of d-axis stator flux ripple, RMS value of q-axis stator flux ripple, and RMS value of total stator flux ripple. And in next lecture and subsequent lectures, we will see that when different PWM switching sequences are applied, how this stator flux ripple gets affected, and which switching sequence gives minimum stator flux ripple and hence minimum current ripple. We'll study more about it, we'll discuss more about it in subsequent lectures. Thank you.